We'll proceed in mind-blowing vector field. So vector field is not only the vector field is, it's not only the algebraic vector, but vector field is something that is related to directional calculus. Whatever we have seen till now is algebra is game, calculus is game of algebra. Calculus is game of algebra. This is what we have seen till now. I'm not saying calculus is not game of algebra, but can you see, like, if I know that iron is a very good metal, iron is a good metal, aluminum is a good metal, then better metal is if we do the alloy. So people achieve many kind of hybrid characteristics through alloying it, mixing 2, 3 metals and then getting the target done. So that is the concept. So vector, you are awesome. Calculus, you are awesome. Now calculus is game of algebra. Then since vector has many features like direction and magnitude, quickly you can get. Whereas algebra has power of function. Algebra has power of function. Function Python function. So function takes independent parameter as function, independent parameter in the function, independent variable as parameter in the function, and then it returns something. So can we mix vector and algebra? If that is true, then that results in vector field. So a vector has components. Typically, it is x component, y component, z component. This is the vector. Now, if x component, y component, z component is a scalar value, then it is called static vector. A static vector in a sense that if I have xy plane and there is a vector, or if there is a x-axis, y-axis and z-axis, then there is a vector. This vector is static in a sense that the end of the vector is a coordinate that is like 2, 3, 4 static. From origin, if I draw, this becomes a position vector, static vector. But what about algebraic vector? Algebraic vector comes into the picture when the x component, if I say my coordinate is 2, 3 and 4, what is position vector? If that is true, then position vector is 2i plus 3j plus 4k. Sometimes it is also called that 2i is a vector along x-axis, 3j is a vector along y-axis and 4k is a vector along z-axis. They combine at origin and then they move in a direction that is 2i plus 3j plus 4k, whatever it is. Now, can I say that the vector is 2xy, 2xyi plus xyj, xyj plus x square, y square, k. Now all three components we see, then they are variable on x and y. Now if I keep changing x and y, consider that I have a xy plane, and if I keep changing x and y here and there, then vector, sometimes it will be like this, somewhere it will be like this, somewhere it will be like this, somewhere it will be like this. So vector is varying depending upon the independent variable. Algebraic functions, they vary dependent upon the independent variable. Algebraic equation is nothing but a function which takes independent variable and then it does the magic. Okay, so that is the scenario. So it takes independent variable and it does the magic. So that is kind of algebraic function. Okay, now what about the kind of hybrid model? Vector, vector and algebraic function. Okay, so vector and algebraic function together. So now the vector has components, x component, y component, z component, or first component, second component, third component, nth component. So these components, they match directly to features in the machine learning. So feature is nothing but if I have a data set and if I have different sample in the data set, one sample is called sample vector document vector. If this is vector, then certainly they are component. The features are component. And then we have lots of vectors that we can draw. Okay, not necessarily that component or feature they are orthogonal to each other. That is the idea. We have to make the features orthogonal to each other. Dimensional reductionability that comes into the picture. Anyway, now if I have a vector that is algebraic vector, then vector would change depending upon the xy in the xy plane. If that is the case, then not only the vector direction would change as per the xy plane, xy value in the xy plane. If somewhere vector is like this, somewhere vector is like, depending upon the xy independent variable. Not only that, every moment, every xy, not only direction would change, its magnitude would also change. Okay, so its magnitude would also change. So vector field is an algebraic vector where each component is a function in algebra, and then that's why changing the independent variables change the vector direction. Not only that, it changes the magnitude of the vector. So this is vector field that we saw. Now comes as that directional differentiation, directional integration. We have done lot in directional derivative along an axis. So if I have a function fxy, if I have a function fxy, then I say that dfxy by dx is partial derivative along x-axis. That is directional derivative of fxy function along x-axis. dfxy by dy is directional derivative along y-axis. If there is any vector u, unit vector, or if there is any vector u on the xy plane, I have two vectors, I vector, j vector, x-axis, y-axis. Okay, for x-axis unit vector is called I. For y-axis unit vector is called j. Now in the same plane I have a vector called u. If I have a function fxy, then what is the dfxy by du? If I do one unit of go one unit of change along x-axis at any point x, then it is dfx by dx. If I go along y-axis at any point y, if I do one unit of change, then how much fxy would change? Dfxy by dy. Now, if I go along unit vector u and along unit vector, if I go along vector u and there is one unit of change at point u, one unit of change, then how much fxy would change? Dfxy by d. This is directional derivative. So this is directional derivative. What about directional integration? Okay, so if I have a function, if I have a function fxy, if I have a function fxy, then if I say fxy dx, fxy dx, then I am trying to calculate the integration along x-axis. Integration along x-axis means if I draw a surface, fxy is a two dimension, three dimension, where the independent component x and y is on xy plane, and for that, yeah, I have fxy value, that is the z value. So dz by dx or dfxy dx, that is directional derivative of fxy along x-axis. fxy dx integration, that is integration of fxy along x-axis, means if I draw the surface and if I take the xz plane, then what is the area? Integration means calculation of the area plainly to its inner depth, that is like that, fxy dy. Or I can say, now consider this is the situation. Now, if there is any vector, if there is any vector u in xy plane, then what is fxy du? Fxy du. So this is called fxy du. Then this is called directional integration. Okay, this is neutral. Directional integration. Okay, let's move ahead because the vector field is the new era. I want vector, I cannot miss out vector because I see everything has a direction now in the world. Market, market to economics to car moving or Formula 1 or Formula 10, Formula 9, I don't know. The football player with number 9 or 10 jersey, everyone is moving. If I say that player in the football, no, he is moving, certainly someone would ask in which direction? In which direction? Okay, so he is moving in somewhat eastward or westward or whatever. At what speed he is moving? Okay, so that is the magnitude. So vector field is direction and magnitude, but vector field is a vector which will keep on changing at x comma y. If football ground or soccer ground has x, all the point, if it is a plane and all the points can be represented through separate x comma y, then at any x comma y, what is the vector of the football player? If I describe, if I know a football player very nicely through artificial intelligence, machine learning, I have database that in this situation, if it takes the football, then how he would move? Then certainly I will have a vector field for that football player. Now I know that what he is going to do. At what moment he is at what x and y. So and then at that moment what is the direction and what is the magnitude, the power he is carrying when he is carrying the football. So this is the future. Okay, function in x and y, and those function in x and y, that is algebraic function, they are now components of a vector. A vector has components, each component is function in x and y. That is vector field. That is nothing but vector field. Now I said fxy dx, that is the integration. Fxy dy, fxy du. Okay, these are not vectors. Since vector field is in future, now can I break this fxy where f is small into vector field, capital Fxy? Okay, so if xy is represented in parametric vector, then xy change into t. Then we call capital F RT. RT is parametric vector. Capital F RT. If it is in xy coordinate, then capital F xy bracket and top arrow sign, that is the vector sign. So capital F top arrow sign, that is the vector sign x comma y. So if capital F is a vector field, then what is this vector field integration along any vector? That is the question. So if I want that, if any vectors integration along any other vector, then what is integration? What is integration? That need to be understood. So this is x-axis. This is x-axis and this is algebraic equation. Algebraic equation is nothing but it's a straight line. This is x-axis, this is y-axis. If this is x-axis, this is y-axis, then I say there is fx, function over x. That function over x, that is the vertical component that is constant along the x. So I call it some constant k. If I draw fx equal to k, then it will come as k is the height then it will come a straight line because at every x, fx is not changing. So here, if this is the origin, then here the fx value is k. Here fx value is k. Here fx value is k. It's a straight line. Then what is fx dx? Fx dx. If this is the origin, then from origin, what is fx dx? Fx dx is nothing but the area. If this is the k line, then k line, if I want till here, till any point x, 0 to x, any point till x if I want, then from x and 0, it makes a rectangle. If it makes a rectangle, then fx dx, that is k dx, is kx, that is the integration, that is the area. So area up till x. So limit is 0 to x. What is the area up, if this is origin, and what is the area up till 10? Then kx is the integration from 0 to 10. That will come as k into 10. That is the area. If it is k, and if vertical is k and horizontal is 10, then area is k into 10. So integration is nothing but it's the area. Area of fx. If this is fx multiplied by the fx, I mean this is fx, that is constant over variation of x. If this is fx, then area is fx height into the width. Fx into x if it is rectangle. So fx into x or fx into 10 is the area. If area fx is a algebraic equation, that every moment the height is changing because it is algebraic, like sin x, e to the power x, ln x, log x. If this is the if this fx is changing everywhere, then at every moment x vertical is changing. In that case, how we can calculate the area? I have to do the integration again. There are ready-made solutions for it, so that complex area also I can calculate. But at the end, it is horizontal into vertical one. If I calculate average vertical, if it is like this line, if I calculate average vertical, then vertical into horizontal. That is the area, that is the integration. Now, question arises is capital F, capital F, capital F du. What is the integration of capital F along any vector u? What is the integration of capital F along, if capital F is a vector field which has only one independent component, then I can say capital F integration side. By default, it is dx. Capital F dx. Capital F dy. If it is one independent component is y. Now there is two independent components, capital F x x y, that is two independent, along any axis, that is any vector, that is u. Earlier we had I vector, j vector, or x axis, y axis. There is any vector u. If that is the case, then capital F, that is the vector field du. If that is true, then consider this is u, this is u. Okay. So if this is u vector, then if there is a fxy, so fxy is nothing but z component, that is vertical component. Now fxy keep changing at each value of the u. Okay. Now if fxy is a vector field, it's not algebraic equation. Means if you consider this is origin, that at origin this is the vector field. If I move along x-axis, okay, consider x-axis, okay, then it will be like this. It will be like this. Magnitude is changing, direction is changing. It is changing like this. Then what is, consider, okay, we'll go back to u vector. Consider this is x-axis. This is x-axis. Now I want vector field f dx. If that is true, then vector field x has first component as x-axis. Leave that also. Now, if consider that vector field is not changing, vector field is a constant vector. Constant vector. Vector field is like this, or vector field is like this. Now, vector field is constant along the x-axis. What is the vector fields? Vector fields integration along x-axis. If I want that, then this vector field has component along x-axis and vector has component along y-axis. Y-axis is orthogonal to x-axis, so this I don't want. What I want is this vector's component along x-axis. That comes as the fx that we were talking about, k. K. K is the algebraic equation we saw, then integration was kx. Now if this is the vector, then vector has two components. Suppose x and y. Then its first component. So this is vector, then its x component. And this is a vector, this is y component. I don't want y component if it is x-axis because it becomes vertical. So if it is vector, then its x component. Whatever x component is coming, now that component into the length. Okay. So if it's this vector's x component, whatever is that, consider it is a constant. So vector is 2i plus 3j. Then vector's x component is 2i, then 2. And then along x-axis up till length 10, 2 into 10. 20 is the answer for the integration. Vector field or vector, if it is a static vector, scalar vector, then its x component, if this is x-axis, I am trying to find integration along x-axis, then this vector's component along x-axis, then this become vector and then multiplied by the length. So that is the height and multiplied by the width. X components y. So y component of this vector means it is like this only. So this and this we don't want. Height and length or width and height is the actual area we are calculating. Width into width cannot be area because it's a line only. So if I take y component, then like this, then it will come as a line. If I take x component, then it will come like this, and then I have the height into. Now, if this is what we did. So if I say x component, if this is x-axis, then this vector dot product along the I vector. If any vector, if I do dot product along I vector, I unit vector, then that is the x component of the vector. If I do dot product along j component, j vector f dot j, vector f dot I vector. If I do vector f dot j vector, then it's y component we are talking. If I do vector f dot I, then we do its x-axis component. So capital vector f dot I, whatever comes, then dx or length. Okay. So this component along x-axis becomes vector f dot I, dot product of two vectors. Then fx component comes into the picture. That x component is an algebraic equation. If that is algebraic equation, then that into the length. So that if I talk in calculus term, then capital F vector dot I vector dx is the integration. If I take this I vector in x, then it becomes capital F dot dx vector is the integration. So this is called vector field line integral or directional integration. Okay, directional integration, this we did the story along x-axis. Consider that this is x-axis, this is y-axis on xy plane, then this is any vector u, x-axis, u vector and y-axis. What is vector field f? What is vector field f? Integration along any vector u, any vector u. If that is the case, then capital F dot du vector integration lower limit to higher limit. This is pure directional integration. capital F, that is vector field, dot dot d u vector, or capital F vector field dot u unit vector d u integration. That is directional integration along an axis, along a vector u. Okay, this is, we have come to arena that we have both the things, directional derivative, directional derivative along a vector u, directional integration along a vector u, both we have seen. Now, if that is the case, then we have seen how we can find it out. Like example, if I take example as I have, this is x-axis, this is this is x-axis, this is y-axis. If this is x-axis, this is y-axis, then there is a line that intercept y-axis and x-axis at 1, 0, at 0, 2. If this is the line, then there is a vector field xi plus yj. There is a vector field xi plus yj. Then what is this vector field's integration along this line? If this is x-axis, this is y-axis, if there is a line, vector field's integration along x-axis, then it is vector field f dot dx vector. Along y, then vector field f dot dy vector. Along this vector, if this is u vector, which has intercept on x-axis as 1, 0, y-axis as 0, 2, then what is vector field f dot du vector? Integration from, if I, now everything is now has direction. Now we have entered into arena that everything has a direction. So if this is the vector u, then it has direction in this fashion, means from 1, 0 to 0, 2. If that is the case, then what is u vector? So that we have to find out. So u vector, how we can denote? Consider now what is relationship between y and x. For any line, y equal to mx, m is the slope or dy by dx, y equal to mx plus y0. Now slope is that if slope is, there is one variation in, or if this is the line and this is the origin, I can take line like this. So if there is -1 variation in x-axis, then there is 2 variation in y-axis. So that is true, then dy by dx is 2 by -1. That would result in -2. So y equal to -2x plus y0, where y0 is the intercept on y-axis, that is 2. So -2x plus 2. So y equal to -2x plus 2. Okay, now consider any point on this line as xi plus yj. Position vector of any point on this line is xi plus yj. Now vector field f dot du vector, integration from 1, 0 to 0, 2 is the line integral of vector field f along vector u. Now vector field equation is xi plus yj dot d of u vector. U vector, I have also taken generic term as xi plus yj. So d of inside bracket xi plus yj, that would result in dxi plus dyj. Now I have xi, vector field xi plus yj dot dxi plus dyj. If I do this, then it becomes x dx plus y dy. This is very, very big thing. Okay, someone really understand this, then he can crack the world. So f x dx plus y dy, where x is the first component of vector field f and y is the first component of vector field f. Or I can say f1 dx plus f2 dy. Since f is I plus xi plus yj, then it becomes x dx plus y dy. If that is the case, then x dx is okay. Now can I convert y to dx one? So it will be easy. So otherwise we have to do in xy plane this integration. Otherwise we can do in x axis only. So if y equal to minus 2x plus 2, then what we are trying now? X dx is okay, y dy. So y I can replace with minus 2x plus 2. And if y is equal to minus 2x plus 2, then dy equal to minus 2 dx. Then minus 2 will come out and it will become like 4x minus 4 dx. 4x minus 4 dx. Here x dx, f1 dx plus f2 dy becomes x dx plus 4x minus 4 dx. If I do, it becomes 5x minus 4 dx. If everything in dx, I can integrate from 1 to 0. So 4x minus 5x minus 4. That would result in 5x square by 2 minus 4x. If that is true, then it would become integration from 1 to 0. Then it would become 5 by 2 minus 4, all negative terms. So that would result in 4 minus 5 by 2. That would result 3 by 2. So this is f function. This is f, the vector field f integration along the line vector u. Okay. Now the question that arises here is that now we have given this example we have tried. So we have given another example that there is a parabola. Same, if this is the u vector, then beginning of the u vector, that is 0 comma 2 to 1 comma 0, there is a parabola whose minimum point is this and it's passing like this. If that is the case, then if that is the case, then this is the line curve. If this is the line curve, then u vector was a straight line. Now u vector becomes a algebraic function. This is vector itself becomes a vector field. So capital F vector dot d u is a vector field now. U vector field integration from, if I go from this side, then 1 comma 0 to 0 comma 2. This is vector field line integral along the parabola. What about if there is a circle like this? One end is here, another end is here. What about another shape? Boss, how it is impossible that someone would calculate line integral with 1000 shape passing from same point to same point. Can I think about path independence? So that comes a terminology called path independence. Whatever the line integral we are talking now, can it be path independent? So if I have beginning point, or if I have a beginning point and end point, and if I have a vector field, then vector field, the integration should depend only upon the vector field, not on the path, taking a straight line, a parabola or circle or whatever. If that is the case, then we have to do some research, because this much we cannot do. We have beginning point, we have end point, path is a straight line or curve or whatever, that should not matter. If I have a particular vector field, in what case it can happen? Now if I say f vector field f dot du, vector field f dot du, integration is small f, because it would result in algebraic equation. It results in small f. Okay. Now can I replace vector field capital F with gradient of small f? Let's try. So now it is capital F dot du vector, capital F vector dot du vector is the integration line integral. Now capital F we are replacing with small f, that is the end result, gradient vector of small f. Since it is a vector, it would replace the capital F. Now gradient of small function, algebraic function f, that is a vector. Gradient vector of small f dot du. Okay. Now u is a vector. Can I change it to unit vector u? I take it out. So gradient of a small f, gradient vector of small algebraic function f, that was the end result of the line integral. Gradient, that is this side, opposite delta. Gradient of a small algebraic function f, that is a vector, dot unit vector along u d of the magnitude of the u vector. That is also a algebraic equation. So if that is the case, then it resulted in this. What is this? If we see that if I have gradient vector of small f, gradient vector of algebraic equation small f dot any unit vector, this is directional derivative of algebraic function f. If I have direction, please watch our videos. So that is like directional derivative along any vector. So if I have directional derivative, if I have a algebraic function small f, and if I want to have directional derivative of a small f along any unit vector, any unit vector, if it is x axis, then it is I vector. If it is y axis, it is j vector. Then along any unit vector u, what is the directional derivative of function f? Then it is gradient vector of f dot product with the unit vector of u. That is what it is. Gradient vector of f dot unit vector of u vector. D after that d and then magnitude of vector u. That is the integration now. If this turns into, now it turns into directional derivative. What is directional derivative? df by du. df by du is directional derivative of function f along vector u or unit vector u. df by du. If I say d of algebraic function f by d unit vector u, then it becomes gradient of f algebraic function, that is gradient vector dot unit vector u. If I do dot product of these two, then it is df by du. So gradient vector of f dot unit vector of u d magnitude of the vector u. So this inside becomes df by du. If it becomes df by du, then integration of df by dx is nothing but f. df by dx is a algebraic function df by dx, and if I try to integrate with dx, then it becomes f itself. So here df by du, doing integration by du, it becomes f itself. What a marvelous research! I have not done this. Okay, whoever has done this, then he is like pioneer. Okay, whoever has done it, then he is the pioneer. Now we turn the capital F vector field dot du vector whole in just one algebraic function f. Okay. Now if I have f, then integration means setting limit from lower limit to higher limit. So if I have algebraic function f, then just set the lower limit and higher limit. So if I had x-axis and y-axis, and this is the path, this is the beginning end of the path, this is the end of the path, then either it is a straight line, or it is a parabola, or it is a circle, or it is any, doesn't matter. Capital F dot du, where u is a vector field of any line, either it's a straight line, parabola, or anything. If I try to line integral this, then that is unrelated to u at all, path at all. It is as good as small f. It becomes a small f. What is small f? Is a small f is an algebraic equation whose gradient vector is capital F. So if I'm able to find a small f, if I'm able to find a small f, that is algebraic function whose gradient vector is capital F, then story is done. Then it is path independent. Because path independent in the sense that line integral of capital F along any path, that is u, that is capital F vector dot du vector, transform into a algebraic function f whose gradient vector is capital F only. So full integration is just related to capital F, not on the u, because whatever result is coming as small f, this gradient vector is capital F, and full I can replace with f with limit begin and begin and end. So the if capital F, if line integral of capital F dot du vector, if it results in an algebraic function f, and f gradient vector, f is a algebraic function, f's gradient vector is capital F, then full integral is nothing but simple f. This proves that gradient of f, gradient of algebraic equation small f, is only related to the vector field f, not on the u. So what I need to find now? I need to find, if I have a vector field v, a vector field f, then I need to find one algebraic equation in the world somewhere whose gradient vector is capital F vector. If I find that algebraic equation, that then full line integral turns into simple f, then lower limit high. Okay, but I have to find the vector, the algebraic function f, that is the constant. If that is true, then this is now consider consider that now it is path independent. There is a point here and there is a point here. This is the 2 point of the path. There is some vector field, magnetic field, vector field, electric field, force field, whatever. And if I want line integral along these 2 points, either it is a line, it is a mesh, it is some zigzag, or it is a parabola, doesn't matter. Only begin point and end point. Two end points, they matter. Then I have to find, for a vector field, I have to find the algebraic function, for which the gradient of the algebraic function is the vector field. Then we are done. Let's try this. That if I have vector field f equal to xi plus yj, then what is its gradient? What is its function? Small f is called potential function. Small f is called potential function. So what is, if vector field is xi plus yj, then what is its potential function small f? So small f's gradient vector is capital F. So df small f, df by dx I plus df by dy j is nothing but f1i plus f2i. So f1 and f2 are first component and second component of vector field capital F. So capital F equal to capital F1i plus capital F2j. Here the gradient field df by d is, for algebraic equation small f, is a small d small f by dxi plus d small f by dyj. If I compare this, then f1 becomes d small f by dx and f2 becomes d small f by dy. If that is the case, then if f1 equal to df by dx and f2 equal to df by dy, then f equal to f1 dx. Again f equal to f2 dy. Same thing, if you remember, sometime back we talked that if I have a vector field f1i plus f2j and dot with du, where u is the line curve that any point I can show as xi plus yj, that then d of u vector converts to dxi plus dyj. If I do dot product, then it turns into f1 dx plus f2 dy. Now that is the first one is nothing, f1 dx is nothing but we call it as f function. f2 dy is again f function, where f function, how it is related is f function, small f. So df by dx is capital F1 and df by dy is capital F2. Both way we are getting it. So how to get f function is f1 dx or f2 dy. Both way I can get the f function. Now if capital F is xi plus yj, then x is the f1. So x dx is the algebraic function f as per the formula. Now y dy is also algebraic function f. Now if I do f1 dx, then x dx would result in x squared by 2 plus any function in y. I say capital C bracket y. Any function in y. So if this is the potential function of small f equal to f1 dx, then x dx x squared by 2 plus I say any function of y. Then if this is f, then df by dx is, if that is x squared by 2, then df by dx is x plus 0, because if it is any function of y, then partial derivative along x-axis is 0. So potential function of small f equal to capital F1 dx, that results in x dx x squared by 2 plus any function of y, that is small f. If I do df by dx, that would result in x plus 0, x, same thing, xi. So now with one way, because f equal to f1 dx, f equal to f2 dy. Through f1 dx, I calculated f as x squared by 2 plus any function of y. If that is true, then what is df by dy? Df by dy is x squared by 2 gone 0 plus dcy by dy. dcy by dc by dy. That is df by dy. df by dy. Now, if I take it y in that direction, then f is again dcy by dy. Means f is kind of cy. We'll try again. So now we have kind of fx potential function f equal to x squared by 2 plus any function c on y. Now if I differentiate with y, then df by dy, df by dy, df by dy equal to x squared by 2 dy, that is 0, plus dc by dy, dc by dy. Now df by dy is the f2. f2 dy is f. Then df by dy is f2. f2 is y, because f is xi plus yj. If f is xi plus yj, then f2 is y and f1 is x. So f2 is y, then y equal to dc by dy, then c is y squared by 2. So if I go by the first integration, that is f equal to capital F1 dx, then now f equal to capital F1 dx, that resulted into x squared by 2 plus any function on y, that is cy. Now here cy came as y squared by 2. Now the potential function is x squared by 2 plus y squared by 2. So potential function exists. Means there is a algebraic function f exists, that is x squared by 2 plus y squared by 2. If I calculate the gradient vector, then it results in xi plus yj, that is a vector field. So this particular vector field is path independent. If it is path independent, then if I calculate this vector field line integral along any line which has begin point and end point, it doesn't matter what path I take. It matters only begin point and end point. If that is true, then if begin point and if this is the if this is the begin point and this is the end point and this is the path, if begin point and end point are same, then the line integral of vector field along this path, it may not be circular, any path, but begin point and end point are same, the line integral of vector field f along any direct line curve u is capital F dot du vector. Now u has no role. Full will be replaced by potential function small f. Okay, since capital F is a path independent vector field, small f and limit from first limit to second, if both limit are same, then this line integration is zero. So in a closed loop, in a closed path where begin and end is same, then vector field line integral is zero. Okay, let's take another example. Y cos xi, vector field is y cos xi plus sin x plus yj. Y